Chapter 34 is on single-phase motors. If you recall, with three-phase motors, there are three types of three-phase motors. However, with single-phase motors, there are many types. We will focus primarily on the split-phase type of single-phase motor. We will cover that in great detail later on in this video. But there are, as you see, several different types of single-phase motors. Shaded pole, multi-speed, repulsion type, synchronous, stepping, universal, servo, and torque. These are all in the textbook, or you can press pause on the video to read the different applications for these. We saw several different types of single-phase motors, and they have specific applications. However, single-phase motors are otherwise almost exclusively used to operate home appliances. And this makes sense because residential power is single-phase. These single-phase motors operate on 120 or 240 volts. Again, this makes sense because residential is single-phase 120 or 240. These motors range from very little horsepower to several horsepower. On D2L, there's a link to a YouTube video called Single Phase Induction Motor. I highly recommend that you watch that video to get a great understanding of how these motors work. We will focus on split-phase single-phase motors and their principle of operation. If you recall, with three-phase motors, when we apply power to the stator, a rotating magnetic field is created. That rotating magnetic field causes the rotor to turn. However, with single-phase motors, if we were to simply apply power, the motor would not start to turn. Single-phase motors need a helping hand to start turning. Once the rotor is turning, however, they will happily continue to turn. So this is a diagram of a split-phase single-phase motor, and we see that there are two windings. There's the start winding and the main winding. And we can see, if you look at this circuit, that they are wired in parallel. They are connected here, and they are connected here. This is a parallel connection. We will talk about the centrifugal switch later in this video, but this switch is actually normally closed. The start winding has relatively small gauge wire. Therefore, it has relatively high internal resistance. The main winding, relative to the start winding, has large gauge wire. And therefore, relative to the start winding, it has relatively low internal resistance. When we apply power to the motor, current flows through both windings because it is a parallel connection. The start winding has small gauge wire, high internal resistance, and therefore the current flowing through the start winding is relatively more in phase with the input voltage. The main winding has relatively large wire and low resistance, so the current flowing through the main winding is relatively more out of phase with the input power. Because the currents flowing through the main and start windings are out of phase with each other, a rotating magnetic field is created. And that is what causes the rotor to turn. Once the rotor reaches approximately 75% of its full speed, we no longer need current to flow through the start winding. That's when the centrifugal switch opens. And at that point, current is only flowing through the main winding, and that is enough to keep the rotor turning.